This part, I'm going to talk about the memory hierarchy. So first, some basics, and I will focus on the so-called SIMD part, single instruction, multiple data part, because actually this SIMD part is the source of performance if you want to get the most from your processor. So first, some basics about the memory hierarchy. So if we want to spend some money, to buy some memory, so the ideal situation is the memory as cheap as possible and as fast as possible, and also as large as possible. But unfortunately, this is impossible because think about it, you want lots of memory, you want to be fast, you want it to be cheap. It's impossible. So that is why we have this hierarchy, so that we can have the best benefit of the combination. So if we look at the value and also the performance of the current memory technology, we will see that first, the so-called SRAM. S stands for static RAM. So basically, let's say the transistors that is built inside your processor. So if you buy a CPU, you have this SRAM inside your CPU. It's not separate from your CPU, let's say. And then DRAM, this dynamic RAM, this is separate. If you pay money, you get this like a stick. So this is dynamic RAM. But if you compare the access time, the dynamic RAM, so basically your memory of the memory of the laptop is much slower than the SRAM, and also the cost is reduced dramatically. So basically, the cost of static RAM is like the cache size. So if you have 1 gigabyte cache, it's going to be very expensive. That's why it's 1,000 royal to 5,000 royal, because it's cache. And for SSD or even for some magnetic disk, the access time is even lower, because I'm not sure if you have the experience with the magnetic disk. It has a rotator. It's very slow. It's mechanic. It has a rotator. It's very slow, but the cost is very low. So because of this memory hierarchy, we are able to have lots of storage for if you have large data, but also for computation, you can utilize the very fast but expensive memory. So this memory hierarchy is needed, and also this hierarchy is useful based on our observation during calculation. So for one calculation, normally we observe that the access of the data is not really very, very global, but somehow localized. And for the localization, there are two important characters. The first character is the temporal localization. So basically based on time. If you are accessing some data, let's say right now, and maybe in 1 second or maybe in 2 seconds, you will access the same data again. So this is the so-called temporal locality. So in this case, if you put this data inside the more expensive but much faster cache hierarchy, namely the cache, memory hierarchy, namely the cache, or even the register, and then you have better performance. This is the so-called temporal locality. And another locality is the so-called spatial locality. For example, if you have an array, I don't know, 100 element, so the observation is normally you access the first part of the array, and then immediately you will access the second part of the memory, and immediately access the third part, or maybe access the first part again of the memory. So you in a very short period of time, you access a limited spatial locality for the memory. So because of those reasons, we need the so-called memory hierarchy and also locality, so that to take advantage of the small amount of fast memory, faster memory, but very expensive, like cache, you heard of cache, and also the so-called SIMD register, which is even faster than cache. And for large amount, but slow memory, we can use it to store very large, for example, matrix, in your calculation. So this shows you the level of memory hierarchy. So the first level, which is very close to the processor, is a so-called SIMD register. So it has a size of hundreds of bytes, very small, only hundreds of bytes, using the static RAM technology, but the access is very fast. And then you have cache. Maybe you heard of L1 cache, L2 cache, L3 cache, and so on. On Noctua 2, one CPU socket has the last level cache about 200 megabyte. It's already very large. So you can have it up to several hundred megabyte. And then for the main memory, normally it's gigabyte or even terabytes for the large memory node, but the access time is slow. And then secondary memory means SSD or the hard drive, mechanical drive, and so on. So to understand the memory hierarchy, it's important to take advantage from the memory hierarchy. So the first level is the SIMD register. So this is inside the CPU core. If you buy a CPU, you have this. For Noctua 2, here you see this is CPU core. There are 8 cores. This is the so-called CCD, one compute complex, as mentioned this morning in the part from Alex. This is one CCD, and this one CCD has it has 16 256-bit vector registers. As you can see, not using byte, but of course you can use byte, and then it becomes even small. So this SIMD vector is, let's say, the power for the so-called vectorization for CPU. It's very fast, but it's very expensive. And then it comes to the L1 cache, L2 cache, which are localized to the CPU core. You can think about this part as this green or this I suddenly forgot the word for this. This is not orange. This is the last level cache is orange. Here it's yellow. Yes, exactly. Yeah, it's apparently I failed in my English examination. Yellow, yes. The yellow part, those are the L1 and L2 cache. And for L3 cache, it's shared by the the CCD. But anyway, the cache is very fast. And then for the entire circuit, you have the so-called memory channel, the main memory, 8 memory channels, let's say 1, 2, 3, 4, 8 memory channels, each for one CCD. This is the hierarchy for the AMD CPU on Noctua 2.